Hi, welcome to Extension 2, Question 12 and Question 15. Starting with Question 12, this year we had an integral which was fairly stock standard. Students, on the whole, could break it into its components that were required, and the integrals were fairly, as I said, stock standard. One was a log and one was completing the square to get an inverse arctan result. And I guess the problems, the most common problems that the students made were in transposition error, having x squared plus 2x plus 3 in the denominator, making the subsequent integrations much more difficult, or not being able to complete the square in the second integral. So these were the two main areas of concern here. I guess for teachers, we just need to make sure we ensure that these types of questions are reviewed, completing the square is practiced, and students take care when writing the question from the paper, most importantly. On the whole, the majority of students found this question pretty easy. Part B was a proof-related question. What is a converse? And show the converse resulting is true. And for 1 mark, the converse was if n is even, then n squared is even. In proving this result is true, if n is even, then we put n equal to 2k, an even number, and carry out the required proof as shown. Some of the problems encountered in part 1, getting confused between converse and contrapositive. In part 2, being able to set up a simple proof about odd and even numbers. And I guess of concern, making simple algebraic errors. For example, 4k squared was equal to 2 lots of 2k. As teachers, we need to make sure the students know their definitions, of course. Similar to last year, they need to know the difference between converse, contrapositive, negation, and counterexample on the whole, and ensuring students that questions can be connected, as in this case, where they are asked, what is the converse? And then to show the converse is true. Again, the majority of students found this pretty easy. Part C was about vectors. We were told the vectors are intersect and are perpendicular, and to find the values of P and Q, noting that this is worth 3 marks. So you can start with either equating the components or the scalar product. If we use the scalar product, R1 and R2 have a scalar product of 0 as they are perpendicular. And so we get 1 times P plus 0 times 3 plus 2 by negative 1 equals 0 for a value of P equal to 2. Because they intersect, then we can equate their components. So we get 3 different equations. Negative 2 plus lambda is 4 plus P mu. 1 is equal to negative 2 plus 3 mu. And 3 plus 2 lambda equals Q minus mu. Solving simultaneously, we can see from equation 2 that mu is equal to 1. Using mu equals 1 and P equals 2, it's pretty easy to establish that lambda is 8, and substituting lambda equals 8 and mu equal to 1 in, we can find Q equals 20. Some common errors: not knowing to use the scalar product on direction vectors only. That's probably the biggest error in this particular question. In equating the y components, many stated that lambda times 0 was lambda. And this led to equations that could not be solved easily and ended up with students giving up after a couple of pages of writing. There were surprisingly simple arithmetic errors, and students ended up with incorrect values for Q, or value for Q, often getting 19 instead of 20. I guess as teachers, we need to ensure that students know for the scalar product, they must use the direction vectors, and students should take care with simple algebraic and arithmetic manipulations. Question caused some difficulty if they could not equate the components or know how to use the scalar product correctly. Part D was an induction using inequality. For the initial case, n greater than or equal to 9, we can substitute n equals 9 and we get the square root of 9 factorial and find 2 to the power of 9. And we can show that the square root of 9 factorial is in fact greater than 2 to the power 9. Alternatively, we could use new number work to prove this, but for the majority, they used calculator. Assuming it's true, and proving true for n equals k plus 1 did cause some concerns. In particular, using the assumption was necessary, and I guess we need to highlight where this has been taking place, and also showing that root k plus 1 is greater than 2 for k greater than or equal to 9, as this is key to getting the 2 to the k plus 1. Some common errors, not many, but some did not prove the initial case. Most, in this case, most used a calculator. Many used the left-hand side minus right-hand side greater than 0 and used the assumption that root k factorial is greater than 2 to the k, but more care and explicit stating that pk is being used shows the logic and process is understood. There was a good deal of fudging and stating that this is clearly a true statement when showing pk plus 1 is true. Quite a number of students neglected to state why root k plus 1 was greater than 2. We need to ensure that students show the initial case is true, no matter how trivial it is. Often in proof of inequalities, there is a tricky inequality step that requires justification, as in this question. Students need to practice these types. And many students need to practice setting out these proofs. They were across the page, they were side by side, and they were very difficult to follow in many instances. Question was well done by most students. Part E was about vectors in 3D, and the first part was to show the result given. From the diagram, it was simple to show that the vector HB is the negative of vector HD, given the information at the beginning that it's a square and they were diagonals. Similarly, HA is equal to minus HC. Hence, we can get HA plus HC is 0 and HB plus HD is 0, which when adding, we get the required result. For part 2 and 3, we needed to use part 1. And so on the left-hand side, we can see GA, GB, GC, GD. And if we write GA as GH plus HA, GB as GH plus HB, and similarly for the rest, adding the left-hand side, adding the right-hand side, we get 4GH plus HA plus HB plus HC plus HD, which of course is the result from part 1, which is 0. Hence, the result becomes evident. For part 2, we know that 4GH plus 4GS is equal to 0, 4GH plus GS is 0, and GS is GH plus HS, so we get 5GH plus HS equals 0, so HS is minus 5GH, which is 5HG, so HG is 1/5 HS, giving lambda 1/5. Quite a number of errors came up in this particular question about vectors in 3D. Using vectors that were not defined made it difficult to know what the students were referring to in their explanations. Show versus describe and explain needs to be understood better. Students should know the difference. In part 2, many simply stated that GA plus GB plus GC plus GD equals 4GH. Not incorrect, but many tried to explain with reference to components vertically and horizontally. There were many ways to show the result, but students need to be careful and not end up with a circular argument. It needs to be clearer. For part 3, many students were blindsided by the 4GH and simply stated lambda was a quarter. Some students' work resulted in negative values, which could often be traced to reverse vectors, i.e. GH is minus HG. For teachers, if defining vectors or labelling diagrams that are not in their solutions, they should copy them for clarity. I suspect many students wrote on their script on the exam paper, but didn't copy this information into their exam booklets. Care should be taken with reversed vectors and ensure that students' answers is the required result. This question was done well by most of the students. A breakdown of question 12 shows we've got some work on calculus, proof, and vectors. Overall, this question was handled well by the majority of students. Moving on to question 15. Our first part of question 15 was a Cauchy inequality style question where the students were given a result and asked not to prove it. It says, using this fact, show that for all non-negative real numbers A, B, and C, the result is true. Many ways to do this question. However, probably the easiest proof involved putting X equal to AB and Y equal to C, and then reapplying the Cauchy inequality a second time to get the required result. Part 2 says using part 1 or otherwise. So the hint is using part 1. So in using part 1, we can also see by rearranging, if the root of ABC is less than a squared plus b squared plus 2c over 4, then the square root of ACB is less than or equal to a squared plus c squared plus 2b, and so forth. By adding these together, we get 3 times the square root of ABC is 2a squared plus 2b squared plus 2c squared plus 2a plus 2b plus 2c all over 4. And when dividing by 2 throughout and dividing by 3, we get the required result. In part 1, some students did not use the given fact as requested to show this result. Some students proved the given result, although it's stated, do not prove this. Some students let C equal AB, which then made the inequality true for specific values, not all values of A, B, and C non-negative and real. Students that used the extended arithmetic geometric inequality without proof were penalised, as they generally did not use the given result as requested. For part 2, most students ignored the use part 1 or otherwise, with those that used part 1 generally getting the correct solution. Lots of strange algebraic inequalities were used to try and get the result. Students that use the extended arithmetic geometric mean inequality were generally very successful and did not need to prove the result in this case. So for teachers, we must ensure that students get plenty of practice at using the arithmetic geometric inequality, extended as well. Know that there will generally be a strong link between part 1 and part 2 in these types of questions. This question was found difficult by the majority of students. For part B, we talked about triangular and hexagonal numbers. And in part 1, it was showed that the odd triangular numbers and so on are also hexagonal numbers. So I guess in choosing an odd number, we either need to choose n equals 2m plus 1 or n equals 2m minus 1. And what we found was by putting 2m minus 1 in, we ended up with the hexagonal number result fairly easily. However, if you choose n equals 2m plus 1, it will work, but there was more work to do. So therefore, the odd triangular numbers are hexagonal. In part 2, which was probably one of the hardest parts of this question, show that the triangular numbers T2, T4, and T6, and so on, are not hexagonal numbers. There were many arguments and methods for doing this. The even numbers 2, 4, 6 can be expressed as 2m. So T2m can be written as 2m squared plus m. Now, we have to use proof by contradiction to show that it's not hexagonal. So we assume it is hexagonal, and we put 2m squared plus m equal to 2k squared minus k. And on rearranging and dividing by k plus m, we see that we get a result that says 1 must be an even number. Clearly 1 is not even, so the original statement is false, and by contradiction, we can prove that result. For part 1, those that used n equals 2m minus 1 were generally more successful than those choosing n equals 2m plus 1. Need to get used to testing both and see which one works best. In part 2, many students chose to stop at 2m squared plus m equals 2k squared minus k without showing that this could not be true and for what values it would hold true, non-integer and negative. I guess our students must learn that n equals 2m plus or minus 1 represent odd numbers, and that n equals 2m represents an even number, and that students cannot just state or assume two expressions cannot equal each other without some sort of proof or contradiction of assumptions. This question was really difficult by the majority of students, especially part 2, where they didn't tend to finish it off. Part C was a mechanics question with a vertical projection of a particle where we needed to show the maximum height was given, as given. So starting with the force equation and noting the direction of the forces and the resistance, and noting that the mass is a unit mass, we end up with dv dt is minus g minus kv squared, which we can then integrate using limits from 0 to t. And we know our initial velocity is u, and at the top it is 0. So integrating both sides, we can get the result which was given. Many students got the result provided, but not necessarily correctly. Part 2, find an expression for the maximum height reached by the object in terms of kg and u, starting with v dv dx this time, and the same force, minus g minus kv squared. Rearranging, this one tended to be done better. And we found the constant. Substituting in, using our log laws, we can get a maximum height when v is 0. So therefore the maximum height, x, is 1 on 2k log g plus ku squared on g, or variations of that result. In part 1, there were some errors and problems. Students did not get far with the incorrect equation of motion. Many students wanted to use m in their equations until they realised m was 1. And students that had a negative in their expression generally lost it, or prematurely or conveniently, as it was not in the required answer. Students that used the definite integral method were generally more successful. For part 2, was generally done better than part 1. Students need to brush up on their log laws, and a few students thought using t from part 1 and rearranging it would lead to the required answer, and for a very small number it did, but it was a much harder problem. Remember to answer the question, put v equal to 0 for maximum height. Ensure that the log laws are well known for rearranging expressions, and make sure that these question types are well rehearsed. Generally speaking, these were the easy marks in this question 15. For part D, we had another proof, but this time it was show that 2 to the n, or prove that 2 to the n plus 3 to the n does not equal 5 to the n for all integers n greater than or equal to 2. Now, proof by contradiction was probably the easiest and most straightforward. And in this case, if we put 5 equals 2 plus 3, then 5 to the n is 2 plus 3 to the n, and then using our binomial expansion, we can note the first and last terms are 2 to the n and 3 to the n, and then there's a host of other terms which are positive. So therefore, 5 to the n is going to be greater than 2 to the n plus 3 to the n. So if it's greater, it cannot equal. And so by contradiction, we have the result. There is an alternative by induction that was common. Proving by induction, we can find P2 is true, assume for PK, and prove for PK plus 1. And we can see in this case that 2 to the n plus 3 to the n is indeed less than 5 to the n. So therefore, it cannot equal 5 to the n as required. Now, we needed to use some form of formal proof here. Students often tried to prove it without any formal proof. Conclusions need to be supported by some form of proof. So when practicing a variety of problem types, it's essential to be aware of possible approaches. Students should know their formula well for binomial expansions. For example, a plus b to the power n and a to the n minus b to the n. And that obviously and clearly do not earn points in a proof. This question was found difficult by the majority of students. And again, a breakdown of question 15 shows that proof was much the greater part of this question, and mechanics made up the easier part of this question. Thank you very much.